quick callback to last time. You stepped up to the free throw line 10 times, and we counted how many you sank. That count was the binomial.
Right. And then we flipped the question. How many shots until your first make? That was the geometric, the weight for one success.
So here's the natural next question. What if you don't stop at the first make? What if you're waiting for your third or your 10th?
And a second twist. What if the things you're drawing don't get put back, like dealing cards or pulling items off a shelf? This is a short one. 2 more discrete families that round out the picture, and then a quick guide to telling all 4 apart.
Let's name the first one, waiting for the kth success.
It's called the negative binomial, and here's its formula. B star of x, k, p, equals x minus 1, choose k minus 1, times p to the k, times q to the x minus k.
And x runs from k upward. K, then k plus 1, k plus 2, and so on. Because x is the trial on which that kth success finally lands, you can't get your third success before the third trial.
One bit of trivia worth knowing. This same distribution goes by another name, the Pascal distribution. Same thing, 2 names.
Now, why that formula? Here's the pattern. The kth success sits on trial x. That last spot is locked. So among the earlier x minus 1 trials, exactly k minus 1 of them were successes.
And a nice sanity check. Set k equal to 1, wait for the first success, and the whole thing collapses back to the geometric. The negative binomial is just the geometric's big sibling.
Let's make it concrete. Flip a fair coin until the third head. What's the chance the third head shows up exactly on the 5th flip?
So k is 3, p is 1/2, q is 1/2, and x is 5.
Plug in. B star is 4 choose 2 times 1/2 cubed times 1/2 squared.
All the halves collect into 1/2 to the 5th, and 4 choose 2 is 6, so it's 6 over 32.
Which is 3/16, about 0.19.
Now, here's a comparison I love. Last lecture, the binomial chance of 3 heads and 5 flips was 10 over 32.
Almost the same, but not quite. And the picture shows why. For the negative binomial, the 5th flip is forced to be the third head. It's locked. So we only get to arrange the other 2 heads among the first 4 flips. That's 4 choose 2, which is 6, not the full 10. Locking that last spot is the whole difference. And if you'd rather not do that by hand, there's no printed table for the Pascal distribution, but GeoGebra's free probability calculator has it built in. One catch worth flagging: GeoGebra counts the failures before the kth success, not the trial number. Our third head on the 5th flip means 2 misses before the third make, so you ask it for x equals 2 with 3 successes and p a half, and it returns 0.1875. Same answer, just be careful what the variable is counting.
On to the second family. This is the one where you don't put things back.
Picture a batch of n items. K of them are what we'll call successes, and n minus k are failures. You scoop out n of them at once without replacing, and x counts how many successes you grabbed.
The probability is h of x, n k, equals k choose x times n minus k choose n minus x, all over n choose n.
And its mean is clean and intuitive. N times k over n, the sample size times the fraction of the batch that are successes.
Let's read that formula in plain language, because it's just counting. The top counts your good draws. Choose which x successes you pulled from the k available, and which n minus x failures from the rest.
And the bottom is every equally likely way to pull n items from n. N choose n. Favorable arrangements over total arrangements. No per trial probability p anywhere, because once you remove an item, the odds shift.
Here's the classic. A lot of 40 items has 3 defective ones. You draw 5 at random, no replacement. What's the chance of exactly 1 defective?
So n is 40, k is 3, n is 5, and x is 1.
Set it up. h of 1 is 3 choose 1 times 37 choose 4 over 40 choose 5.
Crunch the pieces. 3 choose 1 is 3, 37 choose 4 is 66,045, and 40 choose 5 is 658,008.
Multiply the top, divide by the bottom, and you land at about 0.301. Call it a 30% chance the sample shows exactly one defective. The little picture on the right is the whole story. 3 defective, 37 good, scoop out 5.
And again, no table for the hypergeometric, but the probability calculator does it directly. Pick hypergeometric, set the population to 40, successes to 3, sample to 5, ask for x equals 1, and it reads back 0.3011. Matches our hand calculation, and the same buttons give you at most, at least, and between.
Okay, we now have 4 discrete families: binomial, geometric, negative binomial, hypergeometric. How do you tell which one a problem is asking for?
Start by asking, are you counting successes in a fixed-sized batch? If yes, and you sample with replacement, or the trials are independent, it's the binomial.
Still counting successes in a fixed draw, but without replacement. That's the hypergeometric, the one we just did.
But if you're not counting in a fixed batch, you're waiting, running trials until something happens. Then ask, waiting for the first success? That's the geometric.
And waiting for the kth success, negative binomial. Pascal.
So really just 2 questions: fixed number of trials or waiting for a target, and with replacement or without. Answer those 2 and the distribution picks itself.
Let's wrap. 2 new families today.
The negative binomial, or Pascal, for the wait until your kth success.
And the hypergeometric, for counting successes when you draw without replacement.
Put those next to the binomial and geometric from last time, and that's the full set of 4 discrete families, each one answering a different question about yes or no trials.
And here's the big turn coming up. Everything so far has been discrete, probability living on separate bars at whole number counts. Next, we cross over to a continuous variable, where probability becomes area under a smooth curve.
That's Lecture 10, the normal distribution, the bell curve, the standard normal z, and how to read the table. See you there.